All right. Section 9, word problems. Uh, I get mixed messages from students about word problems. On the one hand, people say, hey, what's this useful in real life? Okay, here are some word problems. Oh no, word problems. Mixed messages. Well, okay, mixed signals. Look, and the reason why is that word problems aren't really math problems. They're really translation problems. You translate from English to algebra. You have a word problem, want to find a word answer. But to do that, first you translate to algebra, solve it in algebra, and then translate back. Now this last step, translating back, is generally pretty straightforward. This middle step, solving, well, that's really what this course is about. There's a series of techniques and algorithms that work. This first step, however, is the hardest one. It's the least obvious because algebra is a formal language. It's artificial. It was invented by some very left-brain people. Words problems, however, are in English, which is a natural language. And really, ultimately, it's poetic. The linguist Noam Chomsky often expressed his admiration of the incredible creativity of the most ordinary of everyday utterances. We humans are natural poets. So, but poetry isn't math. Well, they're not the same. And therefore, this is the hard part. There is no formal algorithm for turning a word problem into an algebra problem, because if there were, then it would already be a kind of algebra. To do this, I cannot really properly formalize it. I can, however, give pointers, give suggestive questions to ask. So first of all, here's an obvious one. What is being asked for? I mean, generally in a word problem, they say, what is such and so? So you really want to answer that first off. What is being asked for? And then you give those things being asked for variable names. You can't solve a problem without knowing what you're solving for. And then the next question is, what are you told? What does the word problem specify? Well, the things being specified, those too deserve algebraic names, so you have to assign some parameter names. Then, how do these relate? Again, a fairly obvious question. And so this is the translation part of the translation. You want to do various techniques, draw some diagrams, write up some tables. One useful method is to write something in rhetorical algebra, which is sort of halfway between English and algebra. And then take the next step and write it entirely in algebra. In general, what you do is you want to ask the next question. That's just a series of questions. Chip at it with your questions until you have it down to something that's an algebraic equation. Then solve and translate back. So for example, a rental company charges $65 a day plus 20 cents per mile. Michael rents a truck for 3 days and his bill is $275. How far did he drive? Okay. All right. There are some numbers being told: 65, 2, 3, and 275. All right. How far did we drive? Let's call that little d, the distance driven. There's a charge, 275, so call that letter C. And it's 3 days, so we call it D, the number of days. So the equation is charge equals 65 times the number of days plus 0.20 times the distance driven. What I just literally said is literally rhetorical algebra, because there were words in there. Changing the words to letters, you get C equals 65D plus 0.2D. Okay, now we have an equation. And all right, we substitute some numbers. Capital D, the number of days, is 3. Capital C, the charge is 275. So plugging it in, you get 275 equals 65 times 3 plus 0.2D. At this point, algebra takes over. 65 times 3, that's 195. 275 equals 195 plus 0.2D. Subtract 195 from both sides, you get 80 equals 0.2D. Divide by sides by 0.2, you get 400 equals D. And then translate back. The distance driven was 400 miles. Here's a question about annual interest rates on an investment. It yields 35, it's an investment of $3,500. It yields 262.5 interest in 1 year. Now, all right, here we have to get into some financial math and some financial formulas that we'll see more of later. But there's a principal, in this case, $3,500. There's T for time in years, in this case, 1. There's capital I of the interest, in this case, 262.5. And a little r is the interest rate. It's the one we don't know yet, r. And the formula equals I equals P RT. The interest equals principal times rate times time. Okay, that's a formula that's mentioned in the book, and we'll make use of it here. And we know all the variables except little r. I is 262.5. T is 1, P is 3,500. So plugging these all into here, you get 265, 2.50 equals 3,500 times 1 times R. Divide both sides by 3,500, 262.50 equals 3,500. So R equals 0.075. And since interest rates are usually written in percentages, we rewrite 0.075 as 7.5%. That's the annual interest rate. Oh, and by the way, this formula here, I equals PRT, is actually a use of what's called simple interest. Later, we'll get into compound interest, which is a bit more complicated, involves exponential mathematics, and is one usually in use. Here we have a rectangular garden. It's 25 feet in width, X feet in length, and has an area of 1125 square feet. How long is X? How long is it? The area equals width times length. A equals W times X. A equals 1125. W is 25. So 1125 equals 25X. Divide both sides by 25 and you get 1125 over 25 equals X, which works out to 45. Translating back to English, the answer is, how long is it? It is 45 feet long. Here it's a little, here we're talking about, it's getting a little complicated. 5 rings, each weighs 18 grams, are 10% silver and 90% gold. The jeweler melts them down and adds enough silver to reduce the gold content to 75%. How much silver was added? Okay, the total weight of the 5 rings, 5 times 18 is 90 grams. 10% of that 90 grams is 9 grams of silver. The 90% of 90 grams is 81 grams of gold. So those 5 rings contain 5 grams of silver and 81 grams of gold. So we want to know how much silver was added. Let X be the number of grams of silver added. Okay. Now, 81 grams of gold out of 90 plus X grams in total equals 0.75. That's the fraction, gold over total weight. All right, first transpose 90 plus X. So 81 equals 0.75 times 90 plus X. Then divide by 0.75, 81 over 0.75 equals 90 plus X. 81 over 0.75 turns out to be 108. 108 equals 90 plus X. Subtract 90 from both sides. 108 minus 90 equals X, so X equals 18. So the answer is to add 18 grams of silver. Here we have a shared work route. Candy and Tim share a paper route. Whose name is Candy? Okay, it takes Candy 70 minutes to deliver all the papers, and it takes Tim 80 minutes. Now, let's assume that work rates add if they work together. I'll suppose that Candy works from one end of the route, and Tim works from the other, and they meet in the middle. So the rates add when they work together. And if that's so, then how long will it take them to deliver all the papers if they work together? Okay, here are the equations to use is quantity equals rate times time. Therefore, rate equals quantity over time and time equals quantity over rate. By the way, these three equations are perfect examples of rhetorical algebra. I have words here standing in for variables. Now, her rate was 1 root for every 7 minutes. His rate is 1 root for 80 minutes. Their combined rate, we add those together, 1/70th plus 1/80th of a root per minute, which after some fraction arithmetic is 3/112 roots per minute. The combined time is quantity over rate. Quantity is 1 root. The rate is 3/112 roots per minute. And after canceling roots and inverting this, you get 112 over 3 minutes. So that's 112 over 3 minutes, which is 37 1/3 minutes. 37 minutes, 20 seconds. That's how long it takes them working together. Okay.